Yes, most welcome, sir. Mr. Siddharth, if not
Yes,
allowed,
sir.
please allow sir to. Yes, yes.
Okay.
Okay.
Am I audible to everybody?
Yes, sir.
Yes, yes, sir. Yes, sir. Definitely.
Is the screen visible to everyone?
Yes, sir.
Yes, sir.
Okay. Okay. Thank you so much, Mr. Siddharth. And first of all, I must congratulate my own Department of Biotechnology, University Mullana, for conducting this virtual international seminar on the current scenario of science and technology, where we could see that a lot of eminent speakers, starting from the first day, from our own head of department to the persons from other different organizations from like JNU Delhi, and today we hear from Lucknow also, and from NIT some really informative talk on the science and technology. So without taking much time, I would like to start my presentation on the development of surface functionalized magnetic nanoparticle synthesis, modification, and biomedical application. Okay, so why in the previous talk from the in the morning session, when we were hearing about the functionalized materials from Dr. Raj from NIT, he has already explained a lot about what is the necessity of functionalization and why we want to go with nanoparticle specifically for the functionalization. My talk will be related to the magnetic nanoparticle, how and why we want to modify, and only one biomedical application which I could in my previous work which I have done during my stay at Moscow, Russia. So development of surface functionalized magnetic nanoparticle. First, we need to know what is nanotechnology. That is very important point, because we must know it is a recent multidisciplinary field which is actually consisting of engineering materials and system of the nanometer scale. Okay, so you want to describe its application in medicine or the healthcare, allowing the development of the nanoparticles for drug delivery system, and you want the nanoparticle in the range of 10 to 100 nanometer with a size, ideal size because of the intramolecular uptake, high loading capacity, and specific targeting to the tumor is very important point in designing the nanoparticle for biomedical application. So it has been clearly notified in 1955 by Richard Feynman, a renowned scientist, who during his annual talk at APS, he defined nanotechnology and gave a definition that nanotechnology is actually showing some atomic, molecular, and supramolecular kind of definition, and the application has to be designed on the basis of these properties. So when we talk about nanomaterials, we need to learn some few words. What is nanosuspension, nanoparticle, nanosphere, and nanocapsule? Very little I will speak on these things because when we are preparing nanoparticle, you must have a size of around 10 to 100 nanometer. But when we are going with the nanosuspension, we have a colloidal solution ranging from 1 to 100,000 nanometer. Okay, so nanoparticles for biomedical application, I told you why, because we want the nanoparticle to be delivered at the specific biosystem where you want to utilize. So it should be in the range of 10 to 100 nanometer, and that we call them a nanoparticle. So nanosphere are actually the polymer matrices which in which the drug is actually dissolved or being dispersed in the system, and nanocapsule are the consist of polymer while entrapping an oily core in which the drug is being dissolved. So the nanoparticle has been mainly divided into nanosphere and nanocapsule. I told you, because the matrix reason, you want to incorporate the drug inside, or you want to embed the drug inside the matrix system. And in the nanocapsule reason, where we are preparing the cell system, and you are incorporating them inside, or you are encapsulating them inside the seed system or into the cell system. So the advantage of using these nanoparticles is to improve the efficacy, to reduce the toxicity. You want to increase the enhanced distribution of the nanoparticle, and to improve the improved patient compliances. Actually, when we are talking about the advantage of the nanoparticle, already in the previous uh, presentation, sir has already said the large surface area to volume ratio is one of the important parameter or important property of the nanoparticle. And apart from that, what we need actually is high reactivity of the nanoparticle. We want them to possibly access to all kind of biological system. So biocompatibility with low toxicity is very, very important, and will come only when the enhanced distribution has to be taken place inside the nanosystem. So there are different types of nanoparticle. We have people are working across, like polymeric nanoparticle, solid lipid nanoparticle, nanosuspension, polymeric miscellaneous, ceramic nanoparticles, liposomes, dendrimers, magnetic nanoparticles, nanocell coated with gold, nanowires, nanoprobes, quantum dots, and ferrofluids. The one which I will be targeting is magnetic nanoparticle. Now, most of the researchers from the biomedical applications are basically focusing on the magnetite or magnetic nanoparticle. So we need to know what is magnetite and what is super paramagnetic nanoparticles. So when we are working with the ferrous oxide and asking them to get converted into magnetite, the advantage, there are some advantage and some disadvantage of working with the magnetite nanoparticle. They have a high tendency to get oxidized in the medium, and that is why we are unable to definitely you are able to bound so many functionalization onto the surface of so when you are working with these pions nanoparticle or super paramagnetic iron oxide nanoparticles, you want them you want actually them to provide the magnetic field kind of which, so that they can be aligning in one dimensional. So that makes one difference between the ferromagnetic and super paramagnetic iron oxide nanoparticle, where in presence of external magnetic field you are asking them to align in one medium. So functionalization is very, very important. So why we want to functionalize them, as I have already previously told, that you want a complete like localization of the nanoparticle should be highly effective to the place where you want to concentrate, like you want them not to restrict to different solvent, and you want modification so that the properties like thermal, chemical, optical properties at the surface scale or the biochemistry of that particular nanomaterial can be increased, where the cell where you can hold the solubility and you can reduce the agglomeration behavior. Okay, so functionalization is very, very important. So chemical functionalization of nanoparticle is basically being done to achieve the hydrophobic, hydrophilic, or the conductive behavior of the nanoparticle, because we have to bind, like I told you, either you want to proceed with the nanospheres or with the nanoparticle in the nanoscale, in my previous slide, you want to either embed on the core or inside the cell surface or the sheath. So you have to develop kind of functionalization to get these hydrophobic or hydrophilic conductive nature of these nanoparticles. So functionalization of the surface ligand of the nanoparticle is one of the important parameter, where you want to stabilize these nanoparticle by creating not by disturbing the core of the particle. You want the functionalization so that you can continuously get the exact shape and size of the nanoparticle. Proper functionalization is very important, and you want to prevent the kind of aggregation or agglomeration, where you want these nanoparticle to be in the colloidal nanostructural feature to hold this feature. So by functionalization, you are achieving a lot of biological property, like if you can functionalize these super paramagnetic ion oxide nanoparticle or dual core cell nanoparticle, you are able to bind different drug of the choice for the antimicrobial or anti cancer activity in vitro or in vivo model, because you are asking a ligand or polymer which is actually holding your drug to bind to the surface. So they have the biocompatible nature to which soever receptor they get bound, they are able to release those kind of drug material which you have already bound with the help of functionalization. So a lot of being done in case of quantum dots, where you are able to see that a lot of peptides or kind of drug is being used, and now for binding of these things, different kind of polymers like polyethylene glycol, polypropylene, a lot of things are being utilized. Now, why we want to functionalize these nanoparticles? Today, the world is suffering from a lot of bacterial disorders, and basically we are suffering from the multi-drug resistant because of the phenomena of the bacteria. They are continuously creating illness to the human cells, and they keep on multiplying when they get resistant to the antibiotics. So functionalization in terms of nanomaterial, particularly with the magnetic nanoparticle, and a lot of report or publication has already been published. Even we have also published there also while our working with the magnetic nanoparticles for kind of bacteria, and we could see that quaternary ammonium compounds, which I will show in my further slides, are able to hold the or able to control the biofilm formation of the bacteria. So there are actually three ways of functionalization of the nanomaterial to control the antimicrobial activity. Either you are binding some functional material onto the surface of antimicrobial agent, or you are using some fillers like for example silver nanoparticles inside the capsule system, and asking them to deliver to a particular surface where they will actually bound to the surface. They will disrupt the bacterial membrane. They will bring the kind of stress to the bacterial surface by releasing reactive oxygen species, and thereby they will control the microbial growth. And the third one will be you are using directly some kind of antimicrobial nanoparticle, and you are functionalizing them with the kind of polymer chain, and then you are releasing to the specific target site. So these are the three ways by which we are able to control the antimicrobial activity. Okay. This was one of my paper which I have found most citation, where we have worked with the silver nanoparticle with fluconazole and itraconazole, and we have seen the kind of activity with the fungi, how they are able to control when we have incorporated silver nanoparticle along with the common antibiotic which was being utilized for the control of fungi. So now I'm going directly into the work what we have done. Now we have come across what is nanoparticle, what is magnetic nanoparticle, and why we want to functionalize nanoparticle, and why we want to target the nanoparticle with the microbial cell. So bio-nanosystem is the system where you want your prepared nanoparticle either in the nanosphere range or dual core cell nanoparticle to bind to the specific receptor site and could target the cell, or you can control the biological system. So the work which we have done was able to control the growth rate of Pseudomonas aeruginosa, which we could see is one of the most pathogenous infection, basically being seen where they make the patient immunocompromised and cause a lot of infection, particularly in the lung system. And that is why the work was more or less focused on the Pseudomonas aeruginosa. And there we have done three things. First, how we need to prepare and characterize the super paramagnetic ion oxide nanoparticle, and followed by functionalization of silane modified nanoparticles and pegylation of the functionalized silane modified nanoparticles. So this was the already we have published in the Journal of Cluster Sciences, and even also we have published this entire mechanism in Materials Today Proceeding also, and this is the method what actually being utilized for the chemical method of synthesis of spions, where the reduction hydrolysis pathway is being done, where you are using ferric acetate along with the sodium borohydride in the presence of either you can use organic solvent or the water as a solvent. So you are where we have conducted the experiment. We want the nanomaterial into the conductive form. You want the optical property. You want them to be conductive. So we have used some kind of means we have used toluene, and in presence of that we were able to form the magnetite. I told you what is magnetite and what is the difference between the magnetite and with the super paramagnetic iron oxide nanoparticle. And after getting these this one iron oxide nanoparticle, we have functionalized them. I told you because quaternary this ammonium compounds are very much effective in controlling the biofilm formation, and that is why we have optimized means we have modified the surface with the help of aminopropyl trithoxysilane and with EDS also. And what we have done in the presence of ethanol, we have functionalized the surface with the aptamus, because I told you there are three ways of controlling or releasing the nanomaterial at the bio nanosystem scale. Either you directly incorporate the nanoparticle onto the surface of microbial cell, or in the form of core cell or kind of capsule where you want to release, or you use some kind of ligand or polymer to functionalize the nanoparticle. So what we have done here, we have functionalized the nanoparticle using kind of polymer, polyethylene glycol, and then we have optimized with the amino trithoxysilane. So we have developed two kind of system. One where we have incorporated silane and develop the carboxylic group onto the surface, and the other one we have tried developing the amine group onto the surface in the previous slide, where you can see the amine group was there, and the other one we have developed the carboxylic group. So we want to compare which one is actually able to control the Pseudomonas aeruginosa growth, because we have seen they are the one of the pathogens creating a lot of infection in the lung region. So we have tried growing the Pseudomonas aeruginosa in the laboratory, and we could see how the development took place. But before going into the controlling of the Pseudomonas aeruginosa using these super paramagnetic iron oxide nanoparticle functionalized with silane with carboxylic group, or silane with the amine group, that is quaternary ammonium compounds. So before going into that, we have tried actually we have tried characterizing the size of the nanomaterials what we tried to develop, and we could see that magnetite nanoparticle in the range of the size range was around 16 nanometer. And when we have tried developing the coating kind of functionalization in form of amine or with the help of polyethylene glycol kind of polymer, the size range has little changed, not in key we are not able to utilize that. So the size is very important when you are developing these particles. So dynamic light scattering graph, this is the dynamic light scattering graph. We are able to see the size range, average size range of the nanoparticle. You could see that the size range for silver nanoparticle after optimization, we will see what has happened to that. So when you have prepared the nanoparticle, the reaction kinetics is very important. Why? Because I told you the nanoparticle has to be reactive, has to be dispersed onto the surface. It should be it should not get agglomerated or aggregated inside the system where you want to target. So what we have done, we have tried checking the effect of temperature and the pH, whether the reaction kinetics of these prepared pegylated or amino coated iron oxide nanoparticle has changed drastically or not. So we could see that the zeta potential, which is very important, the charge which is playing a very important role in deciding the biomedical application of the nanomaterials, is highly effective in case of our nanomaterials what we prepared, and the hydrodynamic size was not changing a lot when we tried shifting the pH of the medium, and we could see the stability was highly noticeable in the range of when we are moving into the basic region. So we try to examine the Fourier transform infrared spectroscopy, because you are able to get the finger impression of the biomolecules which are associated with that, and we could see the stretching vibration of amine or carboxylic amine group present in the wave number region of different which we have already found with the help of the library, means kind of um, chemical nature, carbon bond, carbon double bond or single bond, or amine group, primary amine, secondary amine, or tertiary amine. Already it is there. You can compare the things. And we have also conducted the electron microscopy, where we could see the iron oxide nanoparticle getting accumulated inside the sphere system, and you can get to know that how the pegylation has taken place in the third diagram in the C section. You can easily see that how the silane or carboxylic group, we have when you are aware to that, how the core cell is working with that, how the functionalization is working with that, and how the iron oxide is getting incorporated inside that, or how the you are able to achieve the polymer onto the surface, you can see with the help of this diagram. So this is the XRD pattern, which again we have got through, and we could see the crystalline nature of the material, and we have seen for a period of time that the grafting period was retained. So this is one of the important parameter I told you. I tell you because I told you because what is the difference between magnetite and super paramagnetic ion oxide nanoparticle, that in presence of external magnetic field it is holding a universal direction or single direction, and should work as a magnetite. So here we are able to see the saturation magnetization or rancidity or coercitivity of the magnetic nanomaterial, and could see that the nanoparticle showed maximum saturation magnetization of around 70.2 EMU per gram, and that is the advantage. That was the key point of our research, where we could see that how the magnetization was able to hold in the nanomaterial what we have fabricated or what we have functionalized. So this was the overall diagram which we have published this one, and we developed synthesizing of the nanomaterial. It is totally a kind of chemistry concept, but it is very simple. Anybody can do, can synthesize iron oxide nanoparticle and can optimize or can functionalize these iron oxide nanoparticle with aminopropyl triethoxysilane or with carboxysilane. So that is the advantage, and we could, and we have done this comparative analysis by conducting the experiment I told you on Pseudomonas aeruginosa, and we have seen that during the range of the growth kinetics, with the time it has passed through the one you can see in the 96 hours of our study, the iron oxide nanoparticles selenited with amine was able to control the bacterial density in comparison to the carboxylic compound. So this is actually happening. Why? Because the bacterial surface is getting degraded with the amine, quaternary amine compound, as already reported from the this our study. We have also after our study we have also seen some of the studies where people have communicated and got published, and they too have reported these ammonium compounds are actually able to create the permeability onto the surface of the membrane, and they're actually creating the stress to the microbial membrane. So from the overall study we could conclude that it is the spions which are able to control the or which are able to decrease the bacterial presence in the medium, and we could see that the nanofunctionalized nanoparticle were able to go for 100-fold depletion of the bacterial numbers. And this was the study which we conducted for almost 96 hours in the growth kinetics study, and could see. And we have also examined how these nanoparticles are actually disrupting the bacterial membrane in case of Pseudomonas aeruginosa, and we have treated this amino functional as when we have concluded from our study that it is the quaternary ammonium compounds in comparison to the carboxylic group able to disrupt the bacterial membrane, able to get dispersed inside the bacterial membrane and create the reactive oxygen species by creating the stress to the bacterial surface. And then we have gone for the microscopic study of the how the these amino functionalized nanoparticle able to disrupt the bacterial membrane, and you can see how the surface is getting disrupted in case of Pseudomonas aeruginosa. So on the basis of these data, we could come to the conclusion that it is the spions basically with the amine group that are able to interact with the bacterial protein via strong affinity for disulfide or amino group, and can affect the metabolism as well as the redox system of the bacterial cell. To confirm this mechanism, we performed the microscopic analysis, which I showed the slide, and could see how the surface is getting affected. And within the 24 hours of our study, could see the concentration by which the cell was getting disrupted. So amine coated spions attach to the bacterial membrane and disrupt its integrity. Damage to the bacterial cell via electrostatic interaction contribute to increased membrane permeability, perforation of the plasma membrane, and disruption of the cell metabolism. We observed marked changes in the morphological feature of the bacteria in the size and the surface, how it got modified. So we hypothesize that spion's derivative could target a structural protein, potentially protein F, which maintains the shape of the bacterial cell and control the transport of the ions and molecules. This protein has been identified as an important factor contributing to the antimicrobial resistance, particularly in Pseudomonas aeruginosa. So on the basis of uh, this finding, uh, we can conclude that the nanoparticles having superior colloidal stability in the media is the requirement of the is the state of art which we need to develop if you want to control the biofilm formation of any pathogenic bacteria onto the any biosystem where you want to target. So this is very important. You want to develop, or you want to functionalize, you want to make them first of all, you need to study the surface chemistry where you want to develop the either hydrophobic or hydrophilic kind of bond, or the group you want to bond to the surface of the nanomaterial, either in form of polymer or ligand. So this is very important, and we could conclude that these nano probes possess a moderate charge in form of zeta potential, where we studied that either binding with the surface of carboxylic group or with the amine group, was there any surface charge is still holding on to the surface, and we could see that there was a much charge present on the surface even after binding with these compounds. So you want a narrow probes which must contain some kind of charge, and when you are incorporating them into the media, and then only it will bind to the bacterial membrane, because they do carry another charge, and therefore the interaction has to take place. So this study demonstrated that the flexible surface chemistry of the nanoparticle conjugated with biomolecules in a modular fashion has to be developed for the nanoparticle based diagnostic and therapeutic agents. So these are the some papers which we have published. From this is from the publication what we have achieved from our university here from MMDU, and some from our previous organization. Thank you so much.
Thank you so much, sir. I would like to invite Professor and Head Department of Biotechnology, Sharma sir, please say a few words about Dr. Manoj Singh sir.
Excellent presentation,
Please,
Dr.
sir.
Manoj. Yeah, and
Thank you, sir.
thank you for making us aware about many intricacies which we didn't know before. And you have done some excellent work and published in good journals also. And this has lots of promise, as far as I think, in the this nanotechnology area. And I had a small query about this magnetic nanoparticles. That
Yes, sir.
do they have the similar mechanism to counter the antimicrobial resistance? Because what we always think is that slow release and delaying the uh, time and dosage is one of the mechanism that it counters resistance. But is
Definitely,
there
sir,
any
because
other mechanism also from your point of view? Because you showed that this F protein also has some role to play, and
yes,
your
sir, this
particles.
protein actually controls the type and size of the bacteria. So if we can target this protein, definitely you can control the biofilm formation.
Okay, okay. So film
Definitely.
formation
So
and
there are actually three ways which has till now has been reported. Either you go with the core cell formation, either you develop the kind of functionalization onto the surface of bacteria, or you develop like a nanocapsule. मतलब कि तीन तरीके से सर कि एक तो हम सिर्फ बैक्टीरिया के सरफेस पे ही डायरेक्टली फंक्शनलाइज कर दें, या फिर हम कुछ ऐसा मटेरियल बनाएं जो उसको कैप कर सके ताकि वो जब एंटर करे बैक्टीरियल मेम्ब्रेन में तो वो डिस्पर्स ना हो, एक स्पेसिफिक रिसेप्टर साइट पे जाके बाइंड हो. और तीसरा कि आप उसको कोर सेल सीथ के अंदर डेवलप करके उसको रिलीज करें.
ओके ओके.
तो हर एक केस में सिस्टमेटिक इंटरेक्शन होना चाहिए, क्योंकि एक स्पेसिफिक रिसेप्टर साइट से जुड़ना बहुत जरूरी है किसी भी नैनो मटेरियल्स का. इसीलिए काइंड ऑफ पॉलीमर व्हिच वी यूटिलाइज has to be very informative. We have to study the surface chemistry of the nanomaterial, kind of conductive surface है कि हाइड्रोफोबिक बायोमोलिक्यूल्स है या हाइड्रोफिलिक बायोमोलिक्यूल्स किसको होल्ड कर सकता है वो. इसी स्टडी में हमने ये कंफर्म किया कि अमोनियम क्वाटनरी अमोनियम कंपाउंड जो हमने डेवलप किया था पॉलीथिलीन ग्लाइकॉल के साथ, वो बहुत इफेक्टिव है. और उसकी स्टेबिलिटी जब हमने स्टडी की विद रेस्पेक्ट टू द पीएच एंड टेम्परेचर कि उसका जीटा पोटेंशियल होल्ड होना चाहिए, क्योंकि एक सरफेस पे किसी को नैनो पार्टिकल को अगर जुड़ना है तो उसके पास भी अपना एक चार्ज होना चाहिए, क्योंकि ऑलरेडी जो बैलेंस सिस्टम है उसके पास अपना एक डेफिनेट चार्ज है. तो जब तक एक अपोजिट चार्ज उसके साथ बाउंड नहीं होगा, बाइंडिंग विल नॉट टेक प्लेस. So this was the study which we have found that the ammonium carboxylic ammonium group जो long chain of carbon होता है सर, उसकी स्टेबिलिटी ज्यादा बेटर होती है और वो एक टाइम के लिए होल्ड कर सकता है. और द मोस्ट इंपॉर्टेंट पॉइंट की सुपर पैरामेग्नेटिक नेचर भी उसकी होल्ड रहती है, and that is why we were able to study in these things.
And do they have any relation to like you might have heard that many of the drugs, pseudomonas especially, it basically flux out the drug whenever the patient is given the drug, it is effluxed out by the bacteria like pseudomonas. So does this
Definitely sir, this is one of the most
magnetic
challenging
nanoparticles? Okay, yeah, no, it's it has
so far
a
we have
wonderful
not
promise.
seen that. Basically the bacteria have a tendency to go for multi-drug resistance.
Okay, yeah, great. Yeah, it has lots
And
of
that
promise
is why with the
in
nanoparticles
today's
you are
context.
specifically targeting.
Yeah, open to other questions.
Yes,
and
sir.
many
You,
congratulations. Such a lucid presentation, and we are all enriched by your this knowledge and
thank you, sir.
whatever you have imparted through this lecture. Thank you so much.
Thank you, sir.
And
thank you, sir.
many
Thank you, sir.
congratulations for the and appreciation also from Dr. Sushil's side and from all of us.
Yes, sir. Thank
from
you, sir.
the society also for this
Yes, sir. Yes, sir.
fellowship award also coveted on you. Yeah. So
Yes, sir. Yes, sir.
many congratulations. Yeah. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir.
Congratulations, sir. Thank you.
Thank you, sir. Thank you, sir. Okay, Sushil sir, should we are now going for the lunch session, I guess, if there is no question. Dr. Sushil,
Dr. Sushil
I
is
think he
missing
is
from
not
the
there.
scene.
Yeah, he is not there. Siddharth,
Sushil
Sir,
sir.
Siddharth,
sir, I will admit.
if the time, okay,
Yes, sir.
so you can ask him to join. If there is no question from the audience, we can go into the next session after the lunch. If I guess it has
No,
to be
sir.
from your side.
Just a minute, sir. Just a minute. Just a minute. I was
Okay, okay,
disconnected because of some data problem.
okay. No issues, no issues, sir.
Yeah. So we have with us co-convener of the International Virtual Seminar, Dr. Singh sir. I would like to invite him. Please say a few words about the guest speaker, Dr. Manoj Singh sir. Dr. Raj sir, up to you. Dr. Raj
Yes,
sir.
sir.
Yes, sir. Please say a few words about Dr. Manoj Singh sir.
Yes, sir. Yes, sir. Sir, a very excellent and nice lecture delivered by the Dr. Manoj sir. And further congratulate to Manoj sir for their
Thank you,
presentation
sir. Thank you,
and
sir.
being
Thank
a
you, sir.
member of the association. Thank you and all the best, sir. Congratulations.
Thank you, sir. Thank you, sir. Thank you so much. Thank you, everyone.
Now I would like to invite once again Professor and
Okay,
Head
okay, no,
Department of
sir.
Biotechnology.
Already, sir has done. Sir has done.
Okay.
Just
Yeah. As a
just a
formal
second. Yeah.
presentation, let him invite again. Yeah.
Dr. Anil Sharma sir, please felicitate to Dr. Manoj Singh sir through the Fellowship of International Association of Zoologists. Please, sir.
So let me congratulate Dr. Manoj Singh
Yes, sir.
for
Yes, sir. Thank you,
having
sir.
with us and for such a lucid presentation, and also the token of appreciation,
Yes,
this
sir. Thank you, sir.
fellowship for the International Association of Zoologists
Yes,
as
sir.
a fellow of the association. So many congratulations from the core of our hearts to Dr. Manoj Singh. Many
Thank you, sir.
congratulations.
Thank you, sir. Thank you so much, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, Dr. Manoj Singh, sir,
Congratulations, sir.
for
Thank you.
giving your precious time with us in the event. Even though
Yes, sir.
we are sorry for the delay of the session because of
No
some
issues, sir.
technical issues, and but still you have given time with us and delivered informative talk. So thank you so much, sir.
Thank
There
you,
is a
sir.
short break for 1 hour. We will meet once again with the next session, and our guest speaker, Dr. Yuyu Django, Usman Umar Django from Nigeria. He will deliver his excellent talk with on microbial consortium in human welfare. I will enjoy with that, and for that very things, we are here with a short break as a lunch. So please allow
Okay,
me
sir.
and the organizing team for a short break, sir.
Let's proceed for lunch, doctors. Yeah, thank you. Thank you, all the participants and all the esteemed speakers and the organizers as well. And have a good lunch, please.
Okay, thank you,
Thank you
sir.
so much, sir.
Thank you. Thank you.
Thank you, sir.